All right. Good morning, everyone. So, welcome to week number 6 of the semester. So, I hope you had a good weekend. So, looking at our slide right now, we are at module 5. Medyo 1 week behind tayo. Pero that's fine because we have one buffer week, which is supposedly next week. So, I think we'll be right on track to finish or to be on schedule. The target is to start numerical differentiation before the reading break, which is fine. Kasi pwede natin siyang simulan next week. The only problem is that we will not have a free week next week for you to work on the problem set because I checked the schedule and it looks like in our course guide the first problem set is scheduled to be on the week of the 25th to the 29th. So that's next week now. And the supposed coverage is the first unit, which is from interpolation until curve fitting that we will discuss today. So pwede pa rin natin i-push through yung problem set number 1 next week so that wala na kayong iisipin over the reading break. So my proposal is we'll have problem set number 1. It will be assigned October 27. That's a Wednesday, 8 a.m. in Canvas. And then I have two options for you guys. Para technically within a weekday yung submission, we can have the deadline on October 29th. That's a Friday, right before midnight. So that will give you 3 days to work on 5 problems, 4 or 5 problems. Ano ko pa siya nagagawa? Pero my thinking is 4 to 5 problems, and the idea is you will have around 1 hour to finish each problem. So you'll need 5 hours at least to finish the entire problem set. Or if you want, I can accommodate submissions, or I can set the deadline on November 1st. That's a Monday, 5 p.m. So that will give you 3 more days para mag-work. Kaya lang non-working days yung October 30 and teka, parang mali. October 29 ay Friday. So 30 ay tama, meron palang 31 ng October. So that will give you 3 more days, but those would be a Saturday, a Sunday, and the holiday Monday. So pero yung reading break naman ay November 2. So yeah. So mukhang okay to. So what do you want, guys? Let's do it October 29th or November 1. Either case, you'll have 4 to 5 problems and approximately 1 hour per problem. So gusto niyo bang tapusin na siya by Friday or extend siya hanggang Monday? Anong gusto niyo? Any suggestion? Wala talaga, guys. So ako
Sir,
na
sa
lang
tingin po, mas maganda Monday na lang po pasahan kasi hindi po namin sure
Okay.
kung ano po yung deadlines namin for that week din.
All right, I see. And you have said. So yeah, I also think that would be better to put it November 1. If you really don't like to work on the weekends or the holiday, pwede niyo naman siyang tapusin by October 29. But just to give others who prefer working on a weekend, para wala na sila masyadong isipin like attending classes and so on, pwede niyo naman tapusin siya by on a Friday. So I'll just schedule it on Canvas. The deadline would be November 1st. That's a Monday. It's a holiday, but I hope you don't mind extra ano na lang to, extra consideration. So technically, supposedly on deadline October 29. If you finish by then, or if you don't want to work over the weekends, then submit it by the 29th. But if you want to give it more time, so ang deadline na lang ay November 1, Monday 5 p.m. Okay? Though it's a holiday, pero I think that would be better to give you more time. But essentially, this will still be 4 to 5 problems, a lot, 1 hour per problem. So i-compile nyo yung mga program na ginamit nyo sa labs or sa lab exercise, baka magamit nyo siya sa problem sets. So yeah, it's mas maganda kung itabi nyo na siya, i-prepare nyo siya, baka kailanganin sa problem set number 1. And the coverage will be until whatever will finish this week or on Thursday. So yun yung magiging coverage. Okay, so but the thing is, you have ang problema ko lang ay merong lab exer due on the 25th. I hope that will be fine. Pero wala, tama ba? Yeah, lab exer 3 will be due on the 25th. That's a Monday. Bibigay ko naman yung bibigay ko naman yung problem set on a Wednesday, so hindi naman sila mag-overlap. And you really have your Monday's lab, October 25, to do the lab exer. Okay, so I think we are on a good schedule. Though it might seem tight, so pero I hope you can manage. All right, so today we'll start module number 5. So here are our objectives. First, we would like to find the best polynomial fit to a given set of data. We will discuss in details how to get the best linear and quadratic fit to a set of data. Then I will describe what you can do in order to extend the methodology if you want higher degree polynomials for the to fit for your given data, or if you want to consider some other functions. Okay. And then we'll do so by exposing you to the derivation of a formula for the best linear and quadratic fit. And hopefully that will prepare you for the second objective, which is to derive a formula for a best formula for the best fit given given data. So baka posibleng hindi linear o quadratic yung pinakamagandang fit dun sa data. So hopefully the derivation that we will do in class will give an idea how to do it if you want, say, an exponential or a logarithmic fit. Okay. And then third, of course, we want you to use curve fitting to solve specific scientific problems. Okay. So you can also consult the book by Atkinson. Dito ko yata binase yung discussion ko about curve fitting. So if you want a more detailed explanation, so you can go to Atkinson. All right, so let's start. Last time, or actually until last week, we were talking about interpolation, right? So ang idea nun ay meron kang given set of data points, gusto natin yung function na mag-approximate dun sa set of data na yon ay dadaan dun sa lahat ng data points, right? And that's basically what interpolation is and what sets it apart from other approximation techniques. Now, nakita natin ano yung error involved sa interpolation, and it is bounded by some error term. And we look at some ways on how to minimize that error term with respect to the L infinity and the L2 norm. Nakita natin na pwede palang piliin natin yung exabytes appropriately in order to minimize the errors whenever we have the chance to really use them as degrees of freedom. However, kung hindi open yung pagpili or hindi isang option yung pagpili ng mga exabytes, another way is to use as many points as we can, right? Kasi pag lumalaki si n, yung denominator na n plus 1 factorial dun sa error term ay lumalaki, and hopefully it will grow faster than all the other factors, which will keep the maximum error down. But again, we encountered a problem with that kasi pag lumalaki pala yung dumarami yung points na ginagamit natin, lumalaki yung degree ng interpolating polynomial, at posible na magkaroon ng Runge phenomenon. Yung Runge phenomenon, nagkakaroon ng wild and crazy oscillation, especially towards the boundary or the endpoints of our interpolatory interval. So nakikita nyo yung nagwi-wiggle yung interpolating polynomial dun sa dulo nung interpolation. So posibleng ganyan yung mga maging behavior niya, taas baba. So malaking change in the values, and usually we don't want that to happen. But if we insist on using a large number of data points, then posibleng mas okay na gumamit ng piecewise interpolants, wherein we paste together polynomials of small degree in order to get a nice interpolant, right? And usually gusto natin maging continuous siya, and often gusto rin natin differentiable. So nakita natin yung piecewise linear interpolant saka yung cubic interpolants or cubic splines from last week. All right? Kaya lang ang interpolation, meron pa siyang isang problema. And this is instability with respect to perturbations in the input data. And that's what we will look at as another major disadvantage of interpolation, which we will try to remedy by using curve fitting. Okay? So to illustrate this problem about instability, ano yung ibig sabihin ng instability with respect to perturbations in the input data? Ito yun, highlight ko lang. The instability with respect to perturbations in the input data, i-consider natin yung function capital F. Yung capital F ay sine of 2 pi x over the interval -1 to 1. And if I want to interpolate it using 22 equally spaced points, of course, we will get a polynomial or an interpolating polynomial of degree at most 21. Okay. So makikita natin yung results sa figure 5. Okay, so figure 5A, ito. So here you will see in figure A, makikita nyo yung graphs ni capital F at saka ni little f. Si little f yung interpolating polynomial. Tapos yung mga circles dyan, they represent yung data points na ginamit ko. So meron akong 22 dots dyan. Sila yung ginamit sa interpolation. So itong interpolating polynomial shown in orange is a degree 21 interpolating polynomial. So kita natin, oh, kahit pala degree 21 siya, maganda yung interpolation kasi looking at figure A, nag-overlap or almost overlapping na si function f at saka si function little f, right? So the function to be interpolated and the interpolating polynomial seems to overlap over the interpolatory interval -1 to 1. So walang Runge phenomenon na nangyari. So we might be convinced na okay pala yung degree 21 interpolating polynomial. And true enough, if you plot the absolute difference, so yun yung nasa figure B, ito yung absolute error function, E of x equals absolute value of capital F minus little f. Kasi mapapansin nyo, ang pinakamalaking value ng absolute difference ay almost 10 to the -8. Which is very small kasi ang magnitude lang naman nung function na in-interpolate natin ay at most 1. So ang error niya ay 10 to the -8, tapos ang maximum value ng function ay 1. So napakaliit nung 10 to the -8 compared dun sa maximum value na 1. So you can think of the relative error to be something like 10 to the -6%. So napakaliit ng error. Kaya naman, overlapping yung function ay yung graphs ni capital F at saka ni little f. So far, we don't have any problem. Nag-work yung polynomial interpolation nicely. Walang Runge phenomenon, even though we use a degree 21 degree polynomial. All right? Kaya lang, ito yung isang problema sa interpolating polynomials. Unstable siya with respect to perturbations to the input data. And this is crucial. Pag sinabi natin perturbation, isa siyang maliit na pagbabago dun sa data points. Okay? So pag perturbation, isipin niya para siyang measurement error. Na halimbawa, nag-measure ka ng length ng isang bagay, of course, the accuracy of your measurement will depend on your measuring device. At wala namang measuring device na perfect. So kahit bumili ka halimbawa sa palengke ng 1 yarda ng tela, alright? So hindi eksaktong 1 yarda yung mapapabigay sa'yo, right? So meron yung measurement error kahit gumamit ng ruler yung nagtitinda. Kasi nga, finite saka imperfect yung measuring devices natin. Or if you're doing experiments, halimbawa, minimeasure mo yung temperature dun sa yung experiment, hindi mo ma-pinpoint yung exact temperature at that particular moment. So there could be some error involved in the measurement. Or kung hindi man siya dahil sa measurement, pwedeng sa computational error. Kung meron kang simulated data, dahil nirun mo yung experiment mo sa isang computer, which is a finite machine, hindi niya nabibigay yung exactong number. Laging up to some decimal digits lang yung nabibigay niyang value. Halimbawa, si pi, hindi niya pwedeng ibigay lahat ng decimal digits ni pi kasi infinitely many yung decimal digits ni pi. Probably your computer will just give you 3.14159265 and then truncated na siya. So nakuha mong data out of your simulation ay truncated to some decimal digit. So ibig sabihin, medyo hindi mo pwedeng i-trust fully yung data. Kasi nga, it could be due to us to round off error or due to measurement error. Tapos ang gusto natin na pag ginamit ko itong data na to, yung makukuha kong approximate function should be close enough to the given function, or close enough if I use to the approximant if I'm going to use exact data. Alright? So yung sinasabi natin stable. Kapag ka nabago ng kaunti yung data, dapat konti lang din yung mababago sa output. Right? Small perturbations or changes in the input will bring about small changes in the output. Yun yung stable. Right? Yun yung konsepto ng stability. So stable, kapag ka small changes in the input, produces small changes or produce small change or small changes in the output. Pag nangyari, binago mo ng kaunti yung input data, pero napakalaki ng pagbabago dun sa output data, yun yung sinasabi natin na unstable with respect to perturbations in the input data. Okay, so I'll try that with this approximation exercise. So kunwari, so ginamit ko exacto na sine 2 pi x for all x's or for the 22 equally spaced points between -1 and 1. Halimbawa, medyo off yung measurement ko. Instead na nakuha ko yung actual function value, saan ko siya dinefine? Yeah. Instead na na-compute ko yung actual function value, which is sine of 2 pi xi, right? So ito yung actual na f of xi. Kunwari, hindi ko perfectly na-compute yung value niya. Halimbawa, nakuha ko yung measurement na to with a noise or a measurement or a simulation error. Pwede natin tawaging noise na lang, of magnitude 10 to the minus 3, right? So si r sub I ay isang random number from -1 to 1. Random number from -1 to 1, i-multiply ko ng 10 to the minus 3. So basically here I will have a noise of order 10 to the minus 2. Okay? Or 10 to the minus 3 at most. Tama ba? So ito ay decimal. So around 0, 10 to the minus 1. So I think this is about 10 to the minus 4 pala na magnitude, right? Kasi yung Ri ay number between -1 and 1. So yung maximum netong noise ay 10 to the minus 3. So pagpalagay natin order of 10 to the minus 3 yung noise. At alam natin yung value ni sine ay between -1 to 1. Tapos yung noise na dinagdag ko ay at most magnitude of 10 to the minus 3. So medyo maliit na itong noise na to compared to the value of the sine pi x. So itong noise ay maliit compared dun sa f of xi. So pag ginamit ko na data points, yung x sabay comma, y sabay tilde, so itong perturbed data, instead of x sabay comma, f of x sabay, kung stable yung polynomial interpolation, dapat magkalapit lang yung functions na makukuha ko before and after the perturbation, right? And let's see if that will happen. But before going there, let's verify na maliit nga lang yung change dun sa data points. So if you look at figure 5.2, makikita nyo yung plot ng original data points versus the perturbed data. Okay? So yung mga blue circles, sila yung original data, yung orange crosses, sila yung perturbed data points. At kung makikita nyo, halos overlapping pa rin naman yung mga data points na ginamit natin. So basically, at least visually, we see na talagang maliit lang yung noise. Maliit lang yung epekto ng noise dun sa data na gagamitin natin dun sa interpolation. All right? And if you're not convinced with a visual experiment or a visual scatter plot of the original versus the perturbed data points, tingnan natin yung relative error. Okay? Is it relative? Let's see. No, this is the absolute error. Ito yung absolute error between the actual function values and the perturbed function values. And we will see indeed na order 10 to the minus 3 lang yung error. Kasi that is by design. Kasi nga yung y sub I tilde natin ay y sub I, the actual function value, plus 10 to the minus 3 times a random number between -1 to 1. So isa lang tong specific experiment. Okay? Kasi kung stable yung algorithm, kahit anong perturbation, kahit anong value ni r sub I times 10 to the minus 3, dapat ang makukuha natin ay malapit dun sa nakuha nating interpolating polynomial little f kanina. Alright? But in this case, if I will consider this perturbed data points, yung mga nasa process, to be my data na ipapasok ko dun sa Lagrange form ng interpolating polynomial, ito yung makukuha ko. Okay? Yung nasa figure 5.3. So yung kulay blue, siya yung algebraic interpolating polynomial that we got using the original data points. Tapos yung kulay orange, siya yung interpolating function or interpolating polynomial g na nakuha ko using the perturbed data points. And you will see the striking difference between these two graphs. Na, okay, satisfied pa rin yung interpolatory condition kasi yung blue, nag-pass through siya dun sa mga circles which represents the original data point. Yung orange na graph, nag-pass through siya dun sa mga x's, which are the perturbed data points. However, there's a striking difference between the two functions, especially at the tail ends of the interpolatory interval. So nakita niyo yung epekto ng maliit na pagbabago dun sa mga data points. Tapos nag-cause siya, kung paano siya nag-cause ng napakalaking at visible change dun sa interpolating polynomial na na-obtain natin. Alright? And this is a sign, or this is enough evidence to conclude na unstable yung polynomial interpolation nung function capital F over the interval -1 to 1. Kasi nga, ginalaw lang natin ng konti yung mga data points, tapos ganito na yung kinalabasan. Ibang-iba na yung interpolatory polynomial na nakuha natin compared to what we got before. Okay? Yeah. And this is implications. Halimbawa, nasa lab ka. Gumagawa ka ng experiment. Kunwari, tungsten emittance. So pagka nagkamali ka lang ng tabulation ng tungsten emittance, totally different na yung makukuha mo na model. Kung sabihin mo yung tungsten emittance, kunwari lang, ay yung mga circles dito. Tapos instead na yung circle yung nasulat mo na data na ipinasok mo dun sa machine natin to get the algebraic interpolating polynomial, ginamit mo yung erroneous data or data due to measurement or to simulation error or human error. Konting-konting mali dun sa pag-input ng data, completely different yung model na nakuha natin. And that's the problem with, or that's one problem with polynomial interpolation. So at least here we have seen that polynomial interpolation using equally spaced data points is numerically unstable. Kasi we have found one specific case kung saan napakalaki ng pagbabago nung nakuha nating model compared dun sa nakuha natin without perturbing the data points. All right? And we'll try to remedy this. Some remedies, huwag kang gumamit ng equally spaced points. Pwede kang gumamit ng Chebyshev o kaya Legendre nodes, which will, I think, most of the times will result to a stable algorithm. Okay? Pero kung wala kang access dun sa pagpili ng mga exabytes, halimbawa, given discrete set of data points lang yan, wala kang choice kundi gamitin yung binigay na data, then most probably it's better to use other techniques aside from polynomial interpolation. Kasi nga, unstable siya, especially if you suspect that your data is subject to noise or was subjected to measurement or simulation error or round-off error. Okay? Kasi yun yung titingnan natin ngayon ng model, yung polynomial fitting. Alright? So, idea ay mag-fit tayo ng isang function dun sa data. Alright? And ang kagandahan nito ay mag-work siya or pwede natin siyang gamitin para sa forecasting. Kasi ang problema natin sa interpolation, ang interpolation ay valid lamang over the interpolatory interval. Okay? So halimbawa, ang interpolatory interval mo lang ay AB, ito yung domain ng algebraic interpolating polynomial na nakuha mo. If you want to approximate the value of your function at a number outside of the closed interval AB, then hindi mo pwedeng gamitin yung interpolating polynomial. Kasi ang domain lang ng interpolating polynomial ay yung interval formed by the smallest and the largest, or the interval between the smallest and the largest interpolatory abscissa. Pag nasa labas ka na ng interval na yon, hindi mo na pwedeng gamitin pang-approximate yung interpolation. Kaya nga, inter yung tawag sa kanya. So may ibang extrapolation techniques like forecasting techniques. And one of them is polynomial fitting, all right, or curve fitting in general. And most of the times, what we use is what we call least squares data fitting. Okay. So least squares data fitting, which is the subject of this module, what we do is we want to get a function out of a family of functions such that minimize yung least squares error. Ano yung least squares error? So ang idea rito, given ka ng data, x sabay, y sabay, I going from 1 to capital N, gusto nating makahanap ng function, all right, out of a family of functions, capital S, so, or script S. So si script S, siya ay family of functions. So mga candidate functions yan. Tapos, pipili tayo dun sa candidate function, sino sa kanila yung may pinakamagandang fit doon sa data points. Given ka ng capital N na data points, x1, y sub, x sub I, y sub I, gusto nating pumili sino dun sa mga members ni script S yung pinakamalapit dun sa data points. Alright? Ano yung criteria natin para masabi na siya yung pinakamagandang fit? Dapat pinakamaliit yung least squares error. Yung least squares error ay summation lamang ng approximate minus the actual given y values, right? So kunin mo lang yung error between your estimate and your actual data, square mo siya, kunin mo yung summation, yun yung least squares error. Okay? So pipiliin natin sino dun sa mga candidate functions, yung may pinakamaliit na e. Siya yung pipiliin natin to be f hat. So si f hat, siya yung best estimate for the given data set among all candidate functions, little f. So ang idea, pipili tayo sino yung mga candidate functions, tapos magde-develop tayo ng ways paano mapipili out of those candidate functions sino yung may pinakamaliit na least squares error. And that's what we'll try to do in the following discussions. Okay? But I hope our goal is clear. Okay ba yan? Clear ba so far? Any questions? Medyo marami akong sinabi tapos hindi ko siya sinusulat in a slides. But that lahat ng sinabi kong yon, sila yung nasusulat dun sa module, alright? So kaya hindi ko na sila nilalagay sa slide. But any questions so far? Or clear ba yung gusto natin gawin? At kung bakit natin siya gagawin, bakit hindi tayo nag-settle sa polynomial interpolation? Okay lang ba so far? So guys, mag-react naman kayo. Okay, so all right. So I hope everything is fine. At least alam nyo kung ano yung gusto natin gawin. Kasi baka sa problem set, more of essay yung papagawa ko sa inyo. So dapat maikwento nyo sa akin or in your own words itong mga pinagsasabi ko to. Baka ang question sa problem set is why don't we settle with polynomial interpolation? Ano yung mga problema with polynomial interpolation? So you should be able to tell me bakit in your own words. All right? Okay. So let's start with, I guess, the most basic, and probably if you took stat courses, encounter nyo na itong least squares linear approximation. Okay. Now, dito sa linear least squares approximation, gagawin natin yung curve fitting, pero isi-set natin si script S to be the set of all linear functions. Okay. So, mga candidates natin ay mga linear functions. Ipiliin natin sinong linear function ang nag-fit best dun sa given data points. All right. So the goal is to select a function of the form mx plus b kasi nga linear function lang siya. Si m yung slope, si b yung intercept, right? We want to choose mx plus b out of all possible linear functions, so out of all the possible m and b's, such that the least squares error is minimized. Dapat si f hat yung magbibigay sa atin ng pinakamaliit na least squares error. So idea is, we want to minimize this error function taken as a function of m and b, right? Kasi sila yung mga unknowns. So pipiliin natin kung sino may pinakamaliit na summation ng f hat of xi minus yi quantity squared I going from 1 to capital N. Ito yung general template natin sa least squares approximation. Pero nireduce na natin. Nagbigay ako ng specific set of candidates. Ang candidates ko lahat ng linear functions. Eh alam ko naman ang itsura ng lahat ng linear functions ay mx plus b. Alright? So I can replace f hat by mx plus b, plug in x sub I, so I get this expression for the least squares error with respect to linear functions. And I want to find m and b so that this guy is minimized. Gusto nating piliin yung unknown parameters m and b para yung least squares error ay minimal. Tapos hopefully sa Math 38, tama nga, sa Math 38, tandaan niyo pa yung paano mag-optimize ng multivariate function. Pero extension lang naman siya ng Math 36. If you remember, it is necessary that at the minimizers, the derivatives are equal to 0, right? Kasi kung nasa minimum ka, alright, ibig sabihin meron ka ritong lowest point, yung tangent line dito ay horizontal, right? So ibig sabihin yung derivative at the minimizer should be equal to 0. Tapos i-extend nyo lang siya sa multivariate dahil si E ay function ng dalawang variables m and b. So kailangan kunin mo yung partial derivative with respect to m and the partial derivative with respect to b. Kapag si m comma b ay minimizer, both of those two guys will be equal to 0, right? Para makuha natin yung critical numbers. Kasi sa minimizers, dapat 0 yung derivatives, right? So here, we want to compute the partial derivatives with respect to m and with respect to b and equate them to 0 to get the critical numbers or the critical points. Ano yung mga BMs na makakasatisfy nito? Actually, hindi pala dapat BM, dapat MB. Kasi MB ko siya define dito, right? So, but I hope you get the idea. Kunin mo yung partial derivative. So, ito yung function E. Kukunin ko yung partial derivative with respect to M. Pag nag-partial derivative ako with respect to M, lahat ng makikita kong variable ay treated to be constant aside from M. So, sa loob siya ng square, so mag-chain rule ako. Partial derivative, bababa si 2 times this guy. So 2 times this guy. Kaya lang chain rule will kick in. I need to take the derivative of the base with respect to m. Si y ay constant with respect to m. Si b ay constant with respect to m. So ang derivatives nila with respect to m ay 0. So matitira na lamang ay ito. Ano ang derivative ni mx sub I with respect to m? Si x sub I ay constant with respect to m. So ang derivative niya lang ay xi. So ito yung partial derivative with respect to m. And we have said a necessary condition para sa mga minimizers, dapat yung partial derivative ay equal kay 0. All right? So and then you can factor out the 0 here, put that in front of the summation. So magiging ganito lang siya. And then we divide both sides by 2. So we get this guy. Okay? Or better yet, I can also write this as sum I from 1 to big N. What? X sub I squared times M plus summation from 1 to capital N xi times B equals summation I from 1 to capital N ng yi's, right? So I just use properties of summation here in order to get this form, right? Then, tingnan natin bawat isang sa kanila. So si M ay unknown, Pero itong multiplier niya ay alam natin kasi given yung x sabay sa problem. Si b ay unknown, pero mako-compute natin yung sum ng mga xi. So that's fine. And then yung sum ng mga yi's kaya nating i-compute kasi yung mga yi's given sa problems. So I guess we are in a good shape with this equation. And let's proceed to manipulating the partial derivative with respect to b. Again, we want the partial of e with respect to b to be equal to 0 to get the critical points. So, computein lang natin yung partial with respect to b. Okay? Now, partial with respect to b, makita natin ay what? Partial with respect to b, so bababa na naman to si 2 in front. So magkakaroon ka ng 2mxi plus b minus y sabay. And then partial nito with respect to b, kasi yun yung sinasabi ng chain rule. Ito ay constant with respect to b. Ito ay constant with respect to b. So ang partials nila ay 0. Partial ni b with respect to b ay 1. So ang multiplier niya lang dito ay 1. Okay. Kaya mas simple yung partial derivative with respect to b. Okay. And then we equate it to 0 because we want to get the possible minimizers. And then play with this equation, you will end up with this guy after some simple manipulations. So this is the second condition that must be satisfied by our minimizer. Okay? Now, ang goal natin, hanapin si M at saka si B. It might be better to consider this equations 5.6 and equation 5.7 in terms of a linear system. Ito yung linear system corresponding to them. Pinagsama ko lang into one system. And I think it's better to look at it in matrix form. Isusulat natin to in matrix form, ganito na yung magiging itsura niya. Okay. Oops. Papansin nyo, pag minultiply nyo itong row na to by the column vector, makukuha nyo itong right-hand side na to, itong left-hand side na to, equal dito, which is just this guy. Also, if you multiply this bottom row by this column, you'll get this guy, and then the right-hand side is still that guy. All right? So, nirearrange ko lang siya talaga in a matrix kasi mas madaling ipa-compute yung solution ng system if you have, say, if you're using MATLAB or you're using Python. Okay? And then, okay lang naman siya kasi itong matrix coefficient ay 2 by 2 lamang. Tapos ito ay constant, ito ay constant, ito ay constant, ito ay constant. So, predetermine yung matrix of coefficients A. Ito rin ay constant, ito rin ay constant. So, siya yung vector of constants B. Tapos, sabihin natin ang unknown ay X. So, meron kang AX equals B. Pwede mong ipa-compute yan kay sa yung programming language so that you get X equals A inverse B. Or kahit nga mano-mano kasi ang inverse lang naman ni A ay madaling computean kasi 2 by 2 lang naman yung coefficient matrix. Alright? Now, lahat ng pairs M, B na nakakasatisfy ng equation 5.9 is a possible minimizer. However, this system of equations will have a unique solution kung ang determinant ni A I is 0. I don't know if you have linear algebra already, pero isa tong sufficient condition para masabi na unique yung solution ng system. Unique yung solution ng system kapag non-zero yung determinant ni A. Okay? Kung nangyayari lang naman, nagiging 0 lang naman yung determinant ni A kapag totoo itong equation na to. Remember, pag compute ng determinant, product na pababa minus product na pataas. Yun yung definition ng determinant. All right? Now, let's see. Kailan ba magzi-zero yung determinant? Magzi-zero lang naman yung determinant kapag lahat ng x sabay sa equal. Magzi-zero lang yung determinant kung totoo si equation 5.10. But it can be shown that equation 5.10 can only be true if all of the exabytes are equal to each other. Pero so, pwedeng maging reasonable assumption na natin siya na yung exabytes ay hindi dapat pare-parehas. Kasi kung pare-parehas yung mga exabytes, then magkakaroon ka ng hindi function yung makukuha natin. Right? So kaya reasonable na sabihin na yung exabytes ay iba-iba. At pag in-assume natin na iba-iba yung exabytes, sure tayo na ang determinant ng coefficient matrix A ay hindi pwedeng mag-equal kay 0. Dahil hindi siya magiging equal kay 0, unique yung solution natin. Dahil unique yung solution, siya lang yung merong horizontal tangent line dun sa graph ng function. So therefore, automatically, siya yung minimizer. Okay? So again, if we will assume that all the exabytes are unique, then ibig sabihin unique yung solution at yung solution na yon, siya yung minimizer ng least squares error. Okay? Now you can ask MATLAB or your programming language to compute for M and B using this, but I guess it's not hard to use Cramer's rule. Saan nyo na-encounter ang Cramer's rule? Meron pa ba kayong college algebra? Or kayo na yung nasa bagong batch na nagsimula na ng calculus sa college? Grabe, snub talaga guys, no? Or nandiyan pa ba kayo? Just let me know if you are still here. So hopefully na-encounter niyo yung Cramer's rule o paano mag-solve ng 2x2 system at least. Kaya niyo naman siyang gawin ng mano-mano. Okay, thank you. Right, so pero kung isosolve niyo siya ng mano-mano, ito yung makukuha niyong formula. You can use Cramer's rule, you can use elimination or substitution. You'll get the formulas in equation 5.11. Itong formulas sa equation 5.11, yung magbibigay sa atin ng M at saka magbibigay sa atin ng B. And we are assured that this choice of M and B will give us the linear function that will fit best the given data x sabay, comma y sabay. Ito na yung best na makukuha natin. All right? So let's look at an example. Hopefully clear yung discussion paano siya na-derive. Don't worry, hindi ko naman papasaulo yung formula. So just make sure that you know how these formulas came about, paano sila na-derive. And then apply lang natin siya to an example. So let's see. So in example 5.1, given tayo ng data na nasa table na to. Kunwari, ito yung data na nakuha natin mula sa isang experiment. All right? There are, I think, 21 or 22 of them. I think 21 of them. All right? Tapos, ang instruction is to first plot the empirical data to see if a linear fit will be good. Kasi ito yung usually first steps sa polynomial fit. Tingnan nyo muna kung ano yung mga posibleng candidate functions na gamitin natin. Ano yung mga functions na posibleng mag-fit ng maganda dun sa given data. And usually, we want to see how the data looks like when plotted in a scatter plot. Para malaman natin ano kaya yung pwede natin gawing candidate functions. Pag nakuha na natin yung candidate functions, saka tayo magko-compute. Ano yung optimum, ano yung best parameters. And then, after makuha natin siya, usually ko-compute natin yung least squares error. Or better yet, we compute the root mean square error, which is just this guy, which you can interpret as the average least squares error all over the set of data. Okay. So tingnan natin. So sisimulan ko yung solution by plotting this data in a scatter plot. So if you do so, you will get this. Ito yung scatter plot ng data from table 5.1. Makikita nyo, mukhang increasing nga yung trend at mukhang yung trend ay pa-straight line. So kung hindi sinabi sa problem na gumamit ka ng linear fit, then kahit hindi siya sabihin, pag nakita mo tong plot ng empirical data, masasabi mo na, okay, mukha siya talagang line or yung trend niya parang isang line. Right? So that will be a clue for you to to go ahead and try a linear fit. And luckily, we have the formula for the linear fit. So, gagamitin lang natin yung formulas from equation 5.11. Ano yung mga kailangan natin from equation 5.11? Sum ng products ng x at saka y's, product ng sums ng xi at saka yi's, and then sum ng xi squareds, and then baligtad pala, sum ng xi squared at saka sum ng mga xi squared. Okay? Tapos sila yung gagamitin ko para ma-compute si M at saka si B. So coming from this data set, pwedeng gumamit kayo ng Excel, pwede kayo mag-calculator, pwede rin kayo mag-MATLAB para ma-compute yung mga kailangan nating values. So kung gagawin niyo yun dun sa data, ang N ay 21, number of data points, sum ng xi ay 63, sum ng xi squared ay 219.8, sum ng y ay 9.326, sum ng products ng x at saka y ay 60.7302. And then we'll use this info into equation 5.11. We get the following values of M. All right. Dito ay dinisplay ko lang yung 6 decimal digits. But in all of my calculations, ginamit ko lahat ng available decimal digits dun sa aking computing device. I don't remember if I used MATLAB or I used Excel here. Pero hindi ko to tinype dun sa program. Ang ginamit ko yung actual na na-compute niya for this guy. Kasi nga posibleng 30 decimal digits yung binigay sa akin ni MATLAB. Ayokong gamitin ito kasi 6 lang to. But for the purposes of illustrating it in the work text, na-force ako na 6 decimal digits lang yung gamitin. Pero in all of my calculations, I use the maximum precision. Okay? So ito yung value ni M, ito yung approximate value ni B. So ibig sabihin yung least squares linear fit is approximately this guy. Okay. Gawin ko pala itong approximately equal. Kasi truncated ito, truncated din ito. Okay. And then to see if f hat is is indeed a good fit to our data, pinlot ko si f hat, yung nakuha nating linear function, against our given set of data points. And you see na, okay, mukhang magandang model para dun sa trend yung linear fit. Okay? So, nakita niyo yung pinagkaiba nung curve fitting sa polynomial interpolation. Yung polynomial interpolation required na dumaan ka dun sa data points. Pero sa approximation, the least squares approximation, hindi required na mag-intersect yung approximating function at saka yung data points. Imagine kung interpolating polynomial to, mukhang ganito yung kakalabasan niya. Smooth, pero posibleng mayroong wiggles, posibleng may wiggles. Ito yung isang interpolating function kasi dumaan siya sa lahat ng data points. Pero itong approximation technique na to, curve fitting, hindi required na dumaan siya sa data points. All that we want is that the least squares error is minimized. Ang kagandahan dito, pwede natin siyang gamitin to forecast the trend. Okay? Diba, gusto kong makita, ano kaya yung posibleng value kapag ang x ay 6? This 6, labas na nung interval containing the smallest and the largest data points. Pero dahil ang minodel natin dito ay yung trend, so global yung pagkaka-measure natin ng error at hindi local dun sa given abscissas, pwede natin gamitin itong linear fit to forecast ano kaya yung magiging value kapag yung x ay equal kay 6. So kung i-extend ko itong line, posible na gamitin kong approximate para sa function value ni 6, itong value na to. And I can do that kasi ito ay isang modeling hindi lamang nung local trend ng data, but also the overall trend, the global trend of the data. Kaya pwede ko siyang gamitin pang forecast, which is an advantage against polynomial interpolation. All right? Another advantage of curve fitting ay hindi siya sensitive dun sa perturbations with respect to the input data. Kasi nga ang nangyayari ay pinapaliit natin yung least squares error. So understandably, pag naging off ng konti yung data points, halimbawa, ito yung mga data points kong ginamit. yung mga may excess. Kung konti lang yung difference niya dun sa original data, then dahil malapit lang siya dun sa mga original data, tapos minimize ko lang yung relative error, yung least squares error, magiging malapit yung makukuha kong bagong curve fit using the perturbed data dun sa original curve fit na nakuha ko without perturbing the data. Signaling the stability of curve fitting or linear curve fitting with respect to perturbations in the data. Okay? So I hope you will allow me to extend 4 more minutes or so. Tapusin ko lang yung example. Gusto ko mapakita sa inyo na mukhang stable nga yung method na to with respect to perturbations in the data. Okay? Now, gano'ng kaganda yung approximation? So pag kinumpute yung least squares error, yung least squares error again ay sum ng f hat of xi minus y sub I, quantity squared, I going from 1 to n. Alright? Ito yung least squares error. Makukompute nyo yan kasi ang kailangan nyo lang naman ay f hat of x sub I. Ipa-plug in nyo yung mga x sub i's dun sa dun sa curve fit minus the actual function values square, sum them up, makukuha natin yung least squares error. Mas gusto kong tingnan ano yung average root mean square error. So ang kukomputean natin ay 1 over n, plus kunin ko yung square root. And this can be interpreted to be the average error. Alright? So yung least squares error, yung value ni E ay 0.6160095. Pero pag kinuha niyo yung square root ng 1 over n times E, kukuha niyo yung root mean square error ay 0.171283. Of course, we want E and R to be as small as possible. So, ang ibig sabihin to, on the average, ang error per data point ay 0.17. However, that will not give us a complete picture. Gaano kaganda talaga yung approximation? Well, instead of just the least squares error or the root mean square error, compute natin yung relative root mean square error. Yung relative root mean square error ay given by this formula. Okay. Now you can interpret this as the average percent error. Okay. So kung compute niyo siya, an average error is about 0.1248. So you can interpret this that on the average, the error is about 12.48%. That might sound large, pero ito na yung best we can using a linear fit. Okay, on the average, 12.48% error. Okay. So the promise of curve fitting ay magiging stable siya with respect to perturbations in the input data. So let's try a quick experiment. Ano kaya yung mangyayari pag pinerturb natin yung mga data points? So if we will perturb the data points, okay, yung data points ng y sub I, lagyan natin siya ng noise, which is a random number between negative 0.1 to positive 0.1. So negative 0.1 to positive 0.1. So ito yung noise na idadagdag ko. And you will see na medyo malaki siya compared to yung nakita natin last time na 10 to the minus 3 dun sa sine and cosine. So ito mas malaki pa. Alright? And then pag isang random experiment, so mag-generate lang ako ng random numbers from negative 0.1 to 0.1, idagdag ko siya sa y sub i's. Ito na yung makukuha kong data points. Okay? Yung blue circle, sila yung original, yung orange crosses, sila yung perturb. And you will see that even the perturbed data points, mukhang okay pa rin yung linear fit. Kasi parang naglalay pa rin sila sa isang line. So, yun yung idea. So, mukhang okay pa rin na gumamit ng linear fit. So, ngayon, gamitin ko yung perturbed data para kumuha ng linear fit. Tapos, ito yung makukuha ko. Okay? So, ito si G hat, yung orange line. Yung orange line, siya yung curve fit na nakuha ko using the perturbed data points. Tapos kung makikita nyo, malapit pa rin siya dun sa mga actual data points. So ang implication niya, kahit kung meron kang maliit na error dun sa measurements mo ng data points, sabihin na instead yung actual data points yung ginamit mo sa fitting, ang ginamit mo ay yung erroneous data, yung error na yung data na merong measurement noise or measurement error, maganda pa rin yung fit with respect to the actual data, right? And if you will do the same error analysis as what we did in the previous example, you will see na si G hat is a good fit to the perturbed data kasi 11% lang yung error ni G hat dun sa actual perturbed data, dun sa perturbed data. So parang on the average, 11% lang yung error ni G hat with respect to dun sa perturbed data points na ginamit natin to get G hat. Okay? Pero pagka kinompute natin, ano yung error ni G hat with respect to the original data points? Kaya ang kinompute ko dito sa R star relative ay error ni G hat dun sa original data. At makukuha nating error ay 12.51%. So ibig sabihin, hindi ganun kalaki yung makukuha kong error. Binago ko ng kaunti yung mga data points, pero nakuha kong model ay accurate up to 12.51%, which is very close kasi ang error dun sa curve fit kung saan ang ginamit ko ay yung actual exact data, tama nga ba? 12.35% or around that value. Sa ko lang sorry, 12.48%. So pag ang ginamit ko ay perfect data, 12.48% yung error. Pag gumamit ako ng perturbed data, okay, nagkamali ako ng konti dun sa measurement ng data, pag ginamit ko yung maling data na yon o yung perturbed data na yon, ang model ko is or has an error of about 12.51%. So makikita nyo, hindi ganun kalaki yung change dun sa accuracy ng model. From 12.48%, the error went up to 12.51%, which is not that big, provided na or knowing na malaki yung change dun sa data points. Kasi yung data points ay ang pinagbago nila ay 3.27%. So pag kinuha ko yung relative error or relative difference between the perturbed data at saka yung actual data, 3.27%. Ito yung pagitan ng actual at saka measure yung data influenced by measurement noise. So 3.27% yung pinagkaiba ng mga data. Pero kahit 3.27% yung pinagkaiba ng dalawang data, parang napakaliit naman ng difference dun sa results. So ang result ay 12.48% accuracy or error, and then the other one has error 12.51%, and that's not too big. Okay. And sure enough, if you will plot the two linear functions, the first one, the blue one, is when we use the actual data. The orange one is when we use the perturbed data. Magkamukha pa rin sila. All right. So that means small changes in the input did not influence the output too much. And we say this is an indication that our algorithm is stable. And this is true to our promise na ang curve fitting ay magandang alternative to polynomial interpolation. Kasi nga ito ay mas stable with respect to perturbation in the actual data. Right? At saka hindi ganoon kahirap yung pag-compute ng data fit, right? Nung curve fit. Kasi we'll just compute a bunch of numbers from the given data, makukuha mo si M, makukuha mo si B, meron kang linear approximant to the given function, which is accurate at around 12%. All right? So I guess that's a good way to it's a good time to stop here. There are some other discussions here in the module. For instance, kinompute natin gaano kalaki yung difference between the two functions f hat and g hat. Here kinompute ko yung ratio between the L2 norm of the difference between f and g divided by the magnitude of f. So this will give us the relative difference between f hat and g hat. Ilang percent yung pinag-iba ni f hat kay g hat. And it says here na it's around 0.93%. So kung hindi kayo convinced na magkamukha si f hat saka si g hat by just looking at the graph, you can argue analytically. Dahil dalawang functions yung pinagko-compare natin, kunin natin yung L2 norm ni f hat at saka ni g hat. Yung L2 norm ni f hat minus g hat, compare dun sa magnitude ni f. Actually, magnitude to dapat ni f hat. So makukuha natin ay 0.0093. So that means ang pinagkaiba lang ni f hat at saka ni g hat ay 0.93% kahit na ang pinagkaiba ng data na ginamit natin to get f hat and g hat is about 3%. So 3% yung change in the input, pero yung change in the output is around 0.93%. So hindi ganon kalaki yung change in the output. So that signals stable yung method natin. And this is theoretically better than what we would have gotten using polynomial interpolation, right? I guess those are the examples for the linear least squares fit. Any questions, guys? I hope the derivation made sense because on Thursday we look at how to derive the quadratic least squares approximation. And then sa XOR yata may pinapa-derive yung about the power function. So hopefully the derivation will be clear so you can do your own derivation. Okay? All right, so any questions, guys? All right, if there are none, then thank you for joining me today kahit na tahimik kayo. But okay, so yeah, I hope you enjoy the rest of the day. Then let's see each other again on Thursday. Bye, everyone.